basics about what a PCB is. So it's my first session as well. So I am just curious to share my knowledge on this topic. So yeah, as Popang was saying, we are like an open discussion for everyone to share knowledge. And so here we thought of, giving insights on PCB exploration to people with like-mindedness. So, okay. Firstly, we'll begin with trying to understand how basically a PCB in real world is made, and then we'll try to understand and replicate its design in KiCad. So KiCad is a amazing open source tool that gives us very premium features like software like RTM providers. So it would be a nice journey to learn and grow along with you all. So let me try to share my screen and maybe begin with my presentation. Okay. If Gopal, can you confirm if my screen is visible?
Yeah, it's perfect.
Uh,
Rest of people also can confirm the chat.
Gopal, can you hear me?
Yes, yes, I can hear you and it's
Okay.
visible.
Okay. Yeah, thank you. Let me just begin. So yeah, today's session would be about kickstarting the KiCad with like hands-on experience. So I'll try to teach you guys a few basics about KiCad and walk you through all the basic stuff so you can try to implement and design your first basic stuff using KiCad. So let's start with what even is a PCB. In the right, so everyone of us have good exposure with electronics. So, and each electronic device holds its heart in a PCB. That's a printed circuit board. So, all we all are familiar with it, I guess, to quite an extent. So, it's basically like a flat board that holds the connections with the I mean, the macro electronics that we have in today's era, right? So, this idea of PCB, it began way back in the 70s and 80s, where people before PCB used to have a point-to-point wiring. So as circuits became more and more complex, they had to be packed together in a closer spaces. So obviously we had a constraint with wiring over there. So it used to be a lot of mess with point-to-point contact wiring. So it was very messy and it was very unreliable to detect flaws. And if you wanted to repair or detect any error in the circuit, it was highly impossible to an extent. To understand and locate the flow of circuit in this such messy path. So this is one of the few examples of point-to-point. Sorry. Point-to-point wiring. So this is how it would look, the circuitry before PCB. So as you can see, yeah, all the drawbacks here, and it was highly impossible to have a structured understanding of the circuit board here. So later on, we began with, etching copper on hard insulated surfaces so we can replicate wiring systems in there. And then slowly that idea turned into, what we call printed circuit boards of today. So let's try to first understand what would a general PCB contain. So, to actually design a PCB in CAD, we would first have, need a real world understanding of how an actual PCB is made and what are different layers in it. Because these are the terms which will be coming across in the software as well in KiCad. And so to avoid all the confusions and all the dilemmas over there, I thought of introducing everyone with what actually a PCB is and how it's made and what are different actual components of it. So it would be a smooth transition when you try to replicate these principles in our software. So basically, a PCB is actually a stack of multiple layers. Uh, so they are different layers, as you can see in this image. So you can think PCB as a classic sandwich. Okay. First layer, which we would have, we call it a substrate. So this is like this, yellowish or greenish material. That's a insulated fiberglass. So it generally goes by this name, FF4. So this is the material that is used as our base in any PCB. So it's highly important because it has this insulating property. So now when we are having these traces of wire running along our PCB, we need an insulator that withstands all the noises and fluctuations in voltages, and it doesn't easily melt down or have short circuits in it. So that's where this fiberglass material comes in. So it's a hard and sturdy material, and this comes as a base. So you can imagine it as our bread in our sandwich. Okay. So with that analogy, we proceed to the next layer. This is the substrate layer, which is FR4. So this gives us our core of the PCB. It gives it the backbone to the PCB. And next we have is a copper layer. So you can imagine it as a filling in the sandwich. So the next layer that comes onto the sandwich, and it's highly important because this is where the good stuff happens of connecting voltages and linking components to each other. So this is our heart of the circuit again. Uh, so this is basically a lamination of a thin layer of copper over the substrate layer. So here you can see the very thin layer over the substrate layer. This is where connection happens. So now we have a third layer that is a solder mask, that you can imagine it as the sauce, on top of our filling. So this actually is a polymer layer. You can imagine it as like a painted layer on the copper. This is actually to protect our copper traces, which we'll come across later. So copper traces are, you can imagine it as wires. You must have seen designs that we are going to show you. These are the copper traces. So to protect them from oxidation and from shoulder splashes. We have this protective layer on top of copper uh, that acts, like sauce in our bread. And final one is the silk screen. So this is a purely human layer to for a human understanding. So this is, you can think of like a sprinkle on the sandwich, like oregano or uh, some flavor enhancer on top. This is just to bring out the best in the sandwich. So this is the layer where we have our labels mentioned and made. So when we try to solder the components together, we know where what should go. So that's our layers in the PCB. And here are a few more terms about PCB. The trace, as I was saying earlier, this is like, that's our wire in the PCB. That's our copper layer, on PCB that is, etched and perfectly made to connect our different components in the PCB. And next comes, there's this term called footprint. So basically, you can imagine footprint as a parking slot for our components. So when you design a PCB, you have to properly define the dimensions of each component. If you have resistors, we have different types of resistors. There are horizontal ones, there are vertical ones, and different materials of resistors. Based on the composition, the dimensions of the resistor changes. So accordingly, we have to adjust our drill holes in our PCB. Uh, we have to adjust our pads in our PCB based on the resistor that we are going to be using, based on each component that we are going to use in our PCB. So to define the impact of the component on our PCB, we have footprints. You can see these are the footprints. They are basically like a parking slot. They give us the outline of the component so that you can have a defined dimension that fits the component that's available in the market. So you design with practicality, not just theory. So that's where understanding of PCB comes into play, really comes into play when you're trying to, design a circuit in KiCad. So yeah, that's what our footprint does. So it gives a particular definition so that you can understand, this is the particular parking slot where our component is going to be. So it could be different for different components. It could be different for different configuration of each component. So we'll see that in our KiCad service. And then coming to components, we have two types of components in PCB. Okay, one is true hole one, THT. That's what we call true hole component, and second one is surface mount. So as the name sounds, okay, the true hole one are the ones that go through the hole, and it's literally like we have these drills and holes on our PCB. So the component fits inside the drill, and it goes to the inside of the PCB entirely through all the layers of PCB. So, a through hole will have an entire section of PCB crossed and it comes behind. And the surface mount one is, of course, it won't pass through like the strands of or the leads of the surface mount one. They don't pass through the PCB. They mount till a certain depth in PCB. They don't pass through. So the through hole one is a concept which is very beginner friendly because again in our PCB we have again multiple layers of conduction. So this diagram is a very simple diagram where you can just understand what are the basic components of it. Now a PCB generally can have multiple copper layers so that there can be multiple layers where conduction is happening. And like you can see here there are multiple layerings of wires in our classical world of point of wiring. So, just to replicate the same thing, when you're trying to do it in a PCB, we try to have multiple layers of conducting copper so that, the traces don't interact with each other and they can pass through each other. So that's what we'll see later in the presentation. So that's where our surface mount ones come into picture. So they are for conducting from one layer to another, so that you can have multiple layer components. And these are general electronics these days. They basically rely on surface mount ones because over there the density of putting all the components together is higher. So basically, through hole ones are very beginner friendly, where you can have one layer or two layers of conducting copper. So it makes an easy way to understand PCB intuitively. So that's where we are going to start our session with today. We are going with THC company. So it's very beginner friendly. So as I was saying, PCB has like multiple layers of copper and multiple insulations in between. So as you can see, there are different traces running down. You can see them in the multiple layers. This is a trace in some level 10, or this is some trace in level 4. So they are basically running in parallel to each other without interfering with each other. So this is where you can have components packed in a very high density. Instead of having CHT components, we have surface mount ones. So and this is another concept of vertical interconnect access, in short VIA. So as I was saying, we have multiple layers. So when we are dealing with a PCB with multiple layers, a through hole one would directly pass through from first layer to the last layer. But the components which are surface mount, they may be uh, up to a certain depth itself. So maybe this level 4 is where this particular component is conducting and carrying signals to another component on level 4. There can be a component on level 2 that is mounted and carrying signal to another component. So that's where it gets highly dense. And you can also have through hole configuration in a multiple layer PCB. So we also have scenarios where we have a mix of both. Suppose USB drives have a mix of both CHT and surface mount ones. So the through hole ones actually provide a higher mechanical support. So for a flash drive where USB is mounted, it needs a good mechanical support because we're going to be pushing it and pulling it out of the socket. So that's where the hybrid concept of through hole and surface mount comes in play. So we'll explore that in coming sessions. And yeah, that was one thing. Oh yeah, another thing that I wanted to tell is, you may be wondering there are multiple layers. So, there could be chances that, this one hole could be conducting to different layers. So that's avoided by, having only one particular conducting layer. As you can see, this copper is only conducting maybe in level 5, it's conducting this to the through hole component. So other levels are insulated. They are not connected to this particular hole or drill, you can say, a particular THC hole. So you can have this configuration made. So this is why making PCBs highly, uh, technical and highly skilled thing to do. So that's how you avoid, connecting to different layers. You can just choose a layer where you have to plan properly to have your components connect. That's about PCB. So these are the few overlays I wanted to talk about, and yeah. So basic idea of how a PCB comes into life. So these are the 5 steps you can think of. So, first one is like, we know that there is a copper lamination. So our substrate layer will have a copper lamination. So that is the first step, whenever you make a KiCad file and, you send to a PCB designer who makes, PCBs for you. They This is the process that they follow to bring that design to life. So these are the 5 steps. So first one would be, they will take your design out and they'll print it out in a particular, sheet of paper, which is resilient. So after, laminating copper on the substrate layer, they etch your design onto the PCB, and this PCB goes through a process of etching, wherein, except for the trace layers that you have defined, so except for this trace layer, all the rest of the layers, the copper is removed away. So that's the basic idea. So as you can see, our trace layers are left out. So this is the trace layer design that we submit in a Gerber file, and except for this layer, the rest of the layer copper is eaten away, so it's etched out, and then we drill our holes basically, and the next step is, drilling holes after etching. Once the design is finalized and etched, and they go through inspection to check if each trace is properly conducting, and if there is no overlay of traces and any flaws in the etching process. So after following through that, they drill holes in the PCB for the THC components or VIAs. And next step again, after you drill a hole, there are insulating layers also. So you have to plate the holes with copper again. So these holes are plated with copper. And finally, the mask and silk screen are applied. So that protects our trace and components. And the silk screen provides us, the guidance of silk screen is basically like the lettering or text that we provide so that we are able to uh, understand which component goes. So that's with understanding of PCB, and we'll proceed with KiCad now. So, so KiCad was, an open source project. It was developed in 1992 by uh, Jean Perez Charles. Apologies for mispronouncing the name. And he was a French university professor. So in 1992 came up with KiCad as an open source project, and currently it's managed by our KiCad developers team, and it attracts large funds from volunteers like the Raspberry Foundation, Raspberry Pi Foundation, and Arduino. So it's a highly regarded software involved of PCB design, and today we'll be starting our PCB design with a basic AC to DC converter. So I guess if I can zoom in, okay. I think it's a presentation. So okay. So today we'll be first making a schematic design of our AC to DC converter. It's a basic circuit. I think most of us are familiar with. It takes in the AC power and with help of diodes and rectifier. Sorry, with help of diode and capacitor, we produce non-fluctuating uh, power response that comes as a DC to us, a DC signal or DC current to us, and that's what we're trying. That's what we'll be trying to replicate in our design today. So, first step would be to make a schematic as shown. So, from there, we'll walk through on how to, make traces and design the PCB. And our final step would be, as you can see, uh, the final 3D output would look something like this, like proper components of diodes and switches connected to it. And this is the design we'll be ending up with. So, we did a few references and yeah, so since KiCad is like an open source, uh, open source software, so everyone can easily install in their PC. So you can go through this link to download it. I would try to show you how it looks like. So this is the site we have. So over here you can just download, choose your operating system and download the latest version. Currently it's KiCad 9.0.6. So download a version that suits your OS requirements and system requirements. And it's hardly, I guess, 1.5 GB or so. It doesn't take much space. So yeah, you can have it in your system and easily download it. It won't be much of an hassle. And our KiCad file should look something like this. This is what we'll end up with. So let's start with hands-on designing. I'll just start the whole project and let's start with new. So when you open KiCad, it will look something like this. So it will basically have your past projects listed down here. So this was the past project I was working on, testing of the KiCad, and uh, excuse me. So when you open the software first, you are, basically thrown up with a lot of things, and you don't have to worry. So on the right, we basically have all the tools that we'll be using later on. So it's like a step-by-step process. So first we start with schematic that I have shown you in the presentation, which looks something like this. Uh, yeah, this is the schematic. This is where we'll draw. Uh, so this is the schematic we'll draw in KiCad itself. So you can also have a schematic file in your system, and you can directly import it. Or yeah, you can start fresh. So we'll be starting fresh, drawing the schematic. And sometimes, your schematic may contain some symbol or some component that you may have to make from scratch. That's where our symbol editor tools comes in handy. So this is for a later on session. We'll start with schematic today with already available components, and then we'll proceed with PCB editor to define our traces and dimensions, and the footprint editor as well, which I've told about. It's like a parking space where you particularly define how and which dimension of particular component would be used. And in the last, we'll generate a Gerber file where from this file, you can export it to any PCB manufacturer and he can get your PCB ready within days. So that's the flow that we'll be going with. So we'll start with a new project. So we'll go to file and click on new, and you will have to define a destination. Uh,
Excuse me.
define it. Yes, yes.
Divyam, can you just not minimize, take your software from full screen to normal mode? I think the
Oh, is it
leftmost
right?
part is missing.
Oh, oh, right. Is it better now or is it
Can
still?
you slide it towards the right? I think edit
Oh,
and all those
okay.
options are not visible.
Oh, okay. Then
Yeah,
thanks for the heads up.
leftmost. I even now also I can't see the keycard symbol. It means I have to pull it a little right.
Right. Is it
Yeah,
better?
yeah, perfect.
Oh, okay. Thanks for the heads up. All right. So, apologies, guys. Yeah, this is uh, the layout that I was talking about. So most of the things are covered in the right hand side, and we have a general files and edit view, all the buttons over here. We start with a new project. Over here, we click on the new project, and yeah, it's we have to first define a location where our project will be stored. So I already have it in a folder where I want. I will just type in the file name. It's starting with .sh3 and once saved, yeah, the location changes to this, and you can see our schematic file is ready to work on along with our PCB editor. We start with our schematic file, double click and open it, and this is the layout you'll get. I think I have to drag the screen like, yeah, I hope it's visible.
Perfect.
Oh, okay, I think we can finish this tab then. Okay, so this is a basic layout of our schematic editor in KiCad. So here you can see we can define dimensions here. It has millimeters, and this is mils, which is like 1,000 times of an inch, and these are inches. We are designing for a PCB, so we'll start with millimeters, and you can have different symbols here. Just most of them may confuse you right now, but as we walk through, you can understand. Uh, and here, basically, to drag and move, you may have to click the middle mouse button, so that moves the you know sheet for you, and left mouse button doesn't move. It basically selects. We may have to use the scroll button or middle mouse button to drag the view, and you can zoom in and zoom out with the mouse button. And yeah, let's start with defining the settings. So here we start. Okay. As you can see, we have a sheet here where we can fill in the details of the project. The file name is autofill. If I want to add the title and everything, I will just go to the file and go to the page settings. Here I get everything. So issue date, I would want today's date. So I can just put this option. It copies the date of today. Title would be AC to PC converter. And you can have a company name at various Qubit, and you can comment anything, maybe set one different comments that you would like. So here you can have the dimensions of the sheet that you want to work in. I'll select by default A4. Orientation would be landscape. You can have different dimensions based on your needs, and that's where I go with OK. So as you can see here, mm, we are already filled. That's where our names come in, the title and everything. Let's start with our schematic design. So to bring in the components, you can choose this option, place symbols option, or you can directly press the button A, on keyboard. So that also works, and that's the same thing. So it generates the list of components from the library. It's loading for now. Let's just let it finish. So it will by default have most of the components that we'll be needing from diodes, capacitors, resistors, LED, and everything. So yeah, here I think it has loaded. 1 second. And okay, we'll first start with our diodes. I'll be using. You can directly define the name. So if you press D, you get a diode. later on you can define which kind of diode you want. Or I'll just directly start with the diode specification. I'll be using 1N4007, this particular diode. So if you type in the specification and you will get the symbol here. So I can zoom in. This is what it will look like, and you can just pressing the left mouse button to place it. Now I'll need four diodes. So schematic, if you can see, we'll need four diodes, uh, two terminal gates, and capacitor, two resistors, and an LED. So I'll just bring them all first. So you if you want to rotate the orientation, you can just hover over the diode and click R. So that gives my orientation, and I can do Control D, hover over it, and Control D to get uh sorry, and do Control D to get another diode, and that's where I'll put my another one, and I'll do Control D again, third diode, Control D, where my fourth one is. Okay. So one thing, now by default our mouse pointer is selected. So when I select, you know, let me just first
One minute.
bring in the
Hello, hello.
yes,
I was
yes.
selecting something on the right.
Oh, is it still hindering?
The right side is now not visible. Ah, yeah, yeah. Oh
Is
my
it
God.
better now?
Okay, yeah, it is better now.
Okay,
Okay, then can you tell how did you get that library? I think that I
right,
got
right,
missed.
right. So I'll come again. So basically, the left-hand side ones are basic ones. You can turn on and off the grid and select the dimension. You can also have, uh, cross rays like that if you prefer. And here is our library. So this is our play symbol uh, tool. You can just press on it, and the library loads. Another shortcut would be just to press uh, the letter A on the keyboard. So that also does the work. That's how it's going to be. And you can again select your pointer back. So once you're selecting a tool, okay, and you press and you left click on the screen, it will directly open the tool again. So that is another thing with KiCad. So I've selected libraries. So if I press left mouse button, it will open the uh, symbols library. So and to drag around, you have to click the center mouse button. You can zoom in and zoom out as usual, and you can just select and for moving you can just select and move with your regular mouse button. I mean left mouse button. Those are the few things. And let me go back and bring in my resistor now. I just left click again and press R to bring my resistor, and I'll just use it randomly 3 or 4 ones. I'll do Control D to duplicate and get another resistor. Uh, you can refer to schematic if you would like to. So yeah, and then we are missing a capacitor, and let's bring a regular capacitor with C, and then here, and we need an LED, and to rotate it again, select the component and just press R. So it has done the operation for me. Just open that and okay, you can press escape to go back to your mouse pointer. So uh, if I want my mouse pointer back, I can press escape and it goes back to it. So that way you won't have to, yeah, accidentally keep opening. Okay, now next part would be, we'll get our input supply and output supply from terminal. So we'll be having our screw terminals here. And let's press A. So I need a screw terminal of 2 into 2. So this is a screw terminal. So I'll get two input lines and two output lines. I'll just select it and I'll just rotate it. Oh, sorry. Yeah. Uh, this is how I've rotated. And I've placed it. I will duplicate it again and bring it to this edge. And rotate. I want the same. So, I want the same symmetry as here. Because later on I'll be connecting terminal 1 to ground. So what I'll do is like, if I want a mirror image on x-axis, I'll just press x. Uh, and if I want a mirror image on y-axis, I'll press y. I wanted this mirror image here. I hope you can see it. You press x, you get on an x-axis. You press y, you get on y-axis. And then it on x-axis, and there it is. So this is just for my convenience of, you know, having terminal 1 as ground. So, if I want to move this component again, I can drag and move, or I can just hover on it and press M. So if I hover on it without clicking and press M, it's just, yeah, move. So now we'll just connect it with our wires. And that's probably control P always works. And that is first to avoid confusion. We just have to put the input terminal back in. There. So this is a schematic. Oh, wait, this is down. And that's a schematic. Uh, Now, basically, in some older versions, I guess KiCad 7. So suppose we have selected these components, okay, and it has auto named it, diode 1, 2, 3, 4. Sometimes it doesn't, okay. It gives a question mark here, like diode question mark, and question mark. So in KiCad 9, there's no such issue, but sometimes you may end up with a situation like that where, the auto naming is not done. So this naming is important because later on, when trying to, uh, in a PCB editor, you will rely on this naming convention from a schematic to properly join the components with traces. So the naming is important. So we have a tool called annotate. So suppose you don't end up with auto-generated numbers for your component. So I got J1 and J2 because I have two J components in R1 and R2. Sometimes it doesn't. So you can just click on annotate and this symbol here, annotate schematic, and it annotates. Our annotation was already complete, but it still gave a message of annotation complete, and yeah. So you can do that to avoid a situation where you don't have naming of components. Uh, okay, the next step we'll proceed with is again, yeah. No, next step we'll proceed with is filling in the values. So yeah, you may have seen I have not given values to the components here. So let's first give them some value so that we can have a proper working component that can relate to real life one. So here let's start with uh, capacitor. You can just double click and we'll have the value here. You can put in the value and this is something 7 or equivalent. And yeah, that's it. Okay, now this resistor has maybe 10 kilo something. 10 kilo ohm resistor and okay, and can have 2 kilo, and I think that's about it. And okay, now we also have to add our ground. So we can take, let me just come again. So here you can place your power symbol. So if you click it, you'll be taken to power symbols directory. You have different power symbol sources. I just need my ground, so I'll just go with GND, regular ground. So just place it on the component. And okay, that was it. So yeah, this is the schematic. So you can compare it with the one we have. So this is the proper schematic. Now, suppose you may have some errors in your circuit and you want KiCad to check for it. So we also have a tool for that. Um, so second, yeah, uh, yeah, this is the one electrical rule checker. So this is like spell checker in your dock. Like if there is some hardware level of errors that you may be committing, it just throws in a error flag. So you can just click on it and run ERC. And you can see there's one error here, and it says, input power pin not driven by any output power pin. So basically, we haven't assigned, we have assigned ground, but we haven't assigned any power pin for it. So that's what we'll be going to do. We'll just uh, go to our selector and we'll assign a power pin, PWR, power flag. So it's not an exactly power pin, but it acts like a flag. So, in technicality, there's no error in it. So we'll just take this and we'll just assign it here. I'll just rotate, just place it on the circuit, no, circuit, and yeah. Now we'll just run it again here and yeah, showing no errors and we are good to go. So this is the schematic now. It's with no error. Now our first step is done. We have defined our schematics. Now second step would be defining the footprint. So you remember our parking slots, right? Now these different components will have their different dimensions. So we'll just go up with our footprint editor. Uh, again, yeah, assign footprint over here. So if you press it, yeah, all your components are loaded here. And you can see diode 1, 2. I hope the screen is aligned. Just align the. Yeah, I guess it's visible now. So on the left, we can select, what library we want our footprint from. And on the right, we have for each of the component, the footprint defined based on the dimensions and the type of component we are going to use. So just a second. Yeah, okay. Sorry for that. Okay, starting with our capacitor. We'll just search here capacitor. So we'll first search uh, capacitor through for THT. So we are using THT capacitor here, and so we'll assign a footprint to our capacitor. I'll just show you for an example. Suppose I have an actual capacitor. I'll just show you how a footprint looks like. This is how it's going to look like. It's going to have the two pins, and it defines the dimensions here. Uh, so it is 11 mm by 8 mm pin. So it's an horizontal configuration. So you can have, shows in the diameter would be, 8 mm and so on. We just need a regular radial capacitor to go with the radial one with, a little tiny dimension, maybe 8 mm. Okay. You can just right click and see the footprint, how it would look like. This is how it would look like. It's a radial capacitor, diameter 8 mm. So that is what it is. You can just move out and check if this is what you want. Uh, Based on the real life capacitor you'll be using, you can of course have it. So you just have to select your capacitor, then select the footprint we wanted, 8 mm, and yeah, it has assigned capacitor rate. So since we have already defined the diode we'll be using, so it has already assigned footprints to it based on the configuration of diode decided. So yeah, we can skip for diode now. We just need LED, and you can search for LED over here for LED through hole THT, and we'll just go with the regular from 5 mm LED. Okay. And here is a regular 5 mm LED. You can just see how it would look like. And yeah, I think this is the one I wanted. And I'll just append that LED here. And I'll just come with the resistor for. Okay, let me go with our terminal. I'll just with our terminal. Um, terminal block. Oh, let you see the. Let me just check. Uh, okay, terminal block. What if we okay. Mm, okay. We want to resistance maybe. We have PHC resistor. Let me come to that first, maybe. And we have SMB resistor. So we need our THC resistor, and we'll just use uh, axial THC. Maybe with something like 15 mm. Oh, I haven't coming up. Okay, coming up there. Uh, this is an alternative symbol you can use. Yeah, I think I'll go with this. You can select both of them. You have to go here, shift and select, and just press. So it applies to both of them. Go back to my search. Law. Okay. Okay, this is the fourth one. Right? This is the two one. This is seven. This is two. You can see. Uh, second. Yeah. Uh, okay. So here, let's use into two terminal block, but this is not the one I want. Let's just use this. Okay, so we're going to stick with this and let's assign to both of them. Come back here, select both the terminal block, hit shift, assign them, and apply and save. So we'll apply our schematic to them. So since we are done, just check again. It has applied. Yeah, all of them have footprints assigned. Now, finally, we can switch to PCB editor. And this is again how PCB editor looks like. So here you have to upload the schematic from the file that we have taken earlier. Mm, Yeah, update PCB schematic.
Hello.
Yes, yes.
Sorry for interrupting. Can you
Yeah,
please come again that footprint assigning step on
right,
one
right.
second?
I'll go back here. So what we did was we were assigning footprints, right? So we go to assign footprint part and uh, we have different sets of capacitors. Like we have axial ones, we have radial ones, and based on our needs and based on the dimension we want, we can assign a footprint to that. Okay. For now, I've taken this particular radial capacitor. Maybe you can, if you want to have a view of how it would look. So it has. Let me just show you. You can go here, select view selected footprint, and this is how it's going to have. The two pins will go through like this, and it's a radial capacitor. It will have a diameter of 8 mm. So that is what we are going to define in footprint. So for each of the components we define. Suppose in resistors, okay, we have different resistors. Some are axial, some are arrays of resistors. You can see they are eight resistors together in an array. If you're wanting to have that connection done, or maybe there are some relay resistors. Okay, probably there is different sectors. Maybe I can show you some horizontal ones. Based on the requirement you have, see, based on the requirement, it has a 50 of length. So based on the requirement, you will be assigning the footprint. So the holes, the pads we call them, they'll be 50 apart. So based on your requirement, you'll be selecting. So based on my requirement, I won't need much distance between them. So I have a 6 0.3 length. So according to your need, according to the specific resistor you'll be dealing with, specific components, you can define the footprint. So once that is done, you just apply and save. Here, your schematic ends. Now, once it has saved and you can close this, you go to our PCB editor. Okay, it's this tool over here. You open it, and from here is where we are going to define the trace. Okay, uh, to each of the pads from footprint, we'll be defining our trace. We'll be connecting them together on how from here it will be looking how it will look on a PCB. So once you're in, I think I'm clear with that part. I'm sorry, I couldn't get your name. So
Yeah, yeah.
okay,
So it's clear. Once we selected that footprint, which
right.
option we have to press? OK
So
or apply, save, schematic, continue?
yeah, you can
I,
apply schematic and continue. You have to choose that option. So once you're
yeah,
done
but
with, yes,
I selected, but the names, that footprint name, detailed description name is not shown in that near that part number. Like 100 microfarad, sorry, 1000 microfarad There are some text now near that
Right.
1000
Okay, you're
microvolts.
talking. It's not assigning footprint properly.
Mm.
Okay. Have you tried with appliance schematic? We go back to our, we select our PCB editor, and once it's selected, a new window opens up, and just make the window. Oh, it's visible. Okay, thank God. Didn't get much differently. Okay. Uh, right. No, we have already saved our, footprint schematic, so we'll just upload it here. Update PCB from schematic, this option. So, update. Then you can close this window, and here you have your schematic. You can roughly place it on the screen. This is a schematic. I'll just bring it to the center. Yeah, just a second, guys. And I hit myself a little if you don't mind. Yeah. So here is our schematic. You can see all the components here. J1, J2, and four diodes, or two resistors, or capacitor, and an LED. Now it's just what we are going to do is we are going to arrange them accordingly. We'll just it's like a rough estimation of design you may have in mind. So I'll just try to show before making it in 3D. We'll just have an overview of I just want both the input and output on the same side. Like based on your design preference, you can arrange them. So I just wanted here the input and output to be on the same side and diode selected. Excuse me. So based on your preference, you can make them, shift them here and there. I think I can still show you a 3D view if I can. Yeah. So based on the current configuration, like this, you can see in the 3D view. But here we still have to, have it properly placed, define our traces, and there are a few more things to define. So I'll just start with, first placing it properly. I'll just select each of the components and take. So here you have to keep in mind, how you'd want your input and output terminals to be. So even that plays a role. Sorry. So I'll just rotate my terminal so that I can, fit the design that I've shown in the presentation. Uh, both the gates over here and diode as well. Oh, sorry, both the gates over here. Diode accelerate and let's rotate. The rotation is the regular one. You can do it with R, like we have learned earlier. What's here? Okay. You can still see the connections we have defined in schematic. They're still there, From J2 to we have here diode connected, and from diode 1 we have diode 2 connected. So I'll just bring it here. You can see the schematic. It will be easier to understand. See, our diode 1 is connected with diode 2 on below. So if I just arrange them, you can see the clear picture. Okay. Okay. Here is what the components are for the time being. You can select multiple and move to. So yeah, this part is little tricky. Just based on your preference, you just have to have schematic in your mind and arrange it accordingly. Yeah, as I said, in schematic, the output was on the other side. Output, terminal. I just wanted it on this side, so I brought it here. Based on your actual design preference. Okay. Yeah, one thing you may have to make sure. So suppose when I keep it on the center, sometimes you just select this middle text and it keeps rotating that. So you may have to make sure you are selecting the entire component, then rotate it, fit your need, and yeah, drag it where you want it. Yeah, sometimes double clicking opens up, the dashboard. From the whole diagram. So, yeah, perfect. Continue. This is oh, bad guys. Sometimes you can just hover over it and use the keyboard button L to move. I guess that does a better work than mouse clicking and accidentally opening the value twice. Okay. Okay. So it's almost similar to the last design. And once arranged, you can have your edge conditions mentioned. So on the right, you have to select edge cut. Okay. This is where we are going to define proper edge dimensions to our PCB. So this is where we'll be fixing the dimension, and based on that, you can again internally arrange your PCB. You can do it, in the you can first define dimensions and arrange. But since we are just doing it for practice, I just have arranged first. So now we are going to define based on our arrangement. I just selected edge cut and then I'll just use this triangle, rectangle tool, and I'll just, define my dimensions as you can see it's defining and have a flexibility of the figure. Okay. One thing, 45.5 and 33. And one thing I wanted to do is, oh, better. Okay. It fits in right here. Now, sometimes we may need PCBs to be mounted somewhere. So we will just have few holes on the edges. We'll just draw circles that will, make our holes in the edges so that we can mount them with a screw if we need it. So I'll just take a circle here. I'll go to my edge and, you can start. Okay, just have to click. We'll have a lovely and defined. Just have to click and go. Click and enlarge it. approximately. So, I think the way to have yeah, you can just oh, yeah, the silk made. We have it from like this. And try to get move it with M and press and remove it. And how it will work. Press and remove. And I hope, yeah, we have defined our, you know, yeah, mounting hole. So here you can just, uh, mount your PCB close to the edge like this and return this any fire. Okay. Yeah. This is the design we are ready with. Now, it's done. Now I'll just move on. Okay. So, and I guess next step, okay. So you can still modify the changes inside if you want. You can just move your component a little to adjust. Uh, that's always the flexibility. So now we'll be defining traces. Let's choose this student. Okay. Before that, I'll have to define my traces. So if I want them on the front copper layer or back, then let's choose the layer front. I'll choose a back copper layer. Okay. Uh, so you just have to choose a layer. So if you want your traces to be made on the front side of the panel or beneath the panel, I've chosen back copper layer BCU. Just choose the layer, take the traces. Now again, okay. In traces, what I want to do is, some traces, like if I show you here, I just select the terminal. And you can see it's a pretty thin line. Okay. If I want to change the thickness of each trace, let's delete it if I want. Yeah. So, if I want the thickness to vary, because, our terminals will bring in DC current and, sorry, AC current and, the cable, power traces should be much thicker than what we'll be using with our resistors and other components. So, that is the plan here. So, if I want to edit the thickness of a trace, you can see here, track class width. So, let's create it here. And then edit predefined sizes. So here you can see the tracks are here. You can define a size here. I want 1 mm for power and zero point 0.5 to connect components. So I've defined two thickness here. I'll press OK. So if you may have missed, I'll just select the trace. From here drop down, I'll edit pre-designed sizes. I can add on the sizes here. So that's what I'm going to do. For power connections, I'll just use 1 mm trace. So you can see 1 mm is pretty thick. Yeah. Okay. So I'll just make connections now. I'll just based on it also has a guiding line. You can see if I select this terminal, tells me it's going to connect here and eventually there. So I can make use of all the guiding lines. First, I'll connect all the terminals. So you may be thinking, I may have to avoid the components, but all I have to avoid is the pad. So I can go through the components here because components will be mounted. I just need to avoid the pad. And so, it doesn't. Yeah. So because it's, beneath, behind this copper layer, so I can go through the components. I just need to connect my pad. It's guiding me how to do it right. And suppose and you now I'll just take all my power sources are connected. I'll go back to resistors and other connectors. So I'll just connect my resistor first. Okay. So now you may have noticed I've left all the ground terminals if you can see. So I've connected all the non-ground terminals and I've left the ground terminals in the capacitor, LED, and the resistors and everything else. So the thought process here is, as I've told you earlier, what they do is like, in general etching process. So this is our entire copper plate, if you may assume. During etching, all the copper is removed except for the traces. Now, in industries, what happens is, if you remove all the copper out, one thing is you're only left with insulating material and the thermal conductivity of the PCB is not achieved. For to let that PCB cool thermally, you may still need the copper. The second most important thing is sometimes when they etch out the copper, okay, so only these blue wires will remain and rest of the copper from the plate is etched out. Sometimes it happens when the traces are fine enough, the traces aren't mapped correctly. Even they wash off during etching. So what they follow in industry is they let the wires be and just they what they define is they define the entire copper what you call it, sorry, getting the term here, pattern. uh, hmm. Okay. So what they do is like we don't want to have that option of having the entire copper removed and only left with traces. What they instead follow is they'll define an outline along the traces. Okay, each of the trace. They just remove the copper from the outline of the trace so that the rest of the plate isn't conducting. So basically, you can think like they're insulating these wires, only the wires. The rest of the plate is copper. So what I'll do is I'll just define my ground terminal to be common with the plate. So by that scenario, I won't have to define traces for the ground terminal. It will be a common plate that will be conducting the ground terminal, and these will act like a wire force, like a wire with an edges. Their edges will be left uh, as insulated. Only the edges will be etched, and the wire will remain. So in the diagram, too, if you can see, I'm not sure. Not all of the diagrams show it rightly. I think the trace diagram I had didn't define it properly. That's what I'm going to follow. I'll just define the area. I'm not sure. So I'll just define the area on the plate where I want the copper to remain back. I'll just define an outline. Yeah. Mm, this outline. Mm, This. um, Uh, yeah. Uh, so I'll just select the fill zone and define it as ground, GN, ground. So if I define it so, it will just take. Now this entire plate is going to change. I think I'm missing something. Think I would something here. I think it could be one second. Just a second. Uh, I'm going to respond to it. I'm sorry so much. Okay. All right. Sorry. Oh yeah, sorry. I really forgot to mention we have to press the button B. My bad. Okay. So after selecting the copper area tool, we just have to define it as ground terminal as we did. In the end, we just have to press B. Apologies from my end. So yeah, as you can see, only the traces you can see here. They are insulated. You can see these layers are removed and they work as normal wiring. And yeah, that's where you have it. And you can have your view here. You can see how it looks and everything. Yeah, this is our final view. We'll have our voltage coming in from here, going to the diodes and then capacitors. The output will light up the LED in process, and we'll have our output from J2 coming out. So this is how it's going to look. And if you want to add some logos or you can add some textual information, let me just okay. Yeah, it's okay. Yeah, if you want to add some logos or anything, we'll come to our front fill screen. So here it is. You can add your text here. You can write the name. If you do converter, and you can place it anywhere on the PCB you want, and define the thickness of it. Can make it thicker with the oh, sorry, with with one thickness would be 0.3. Yeah. So when you define it over there on the so this is done on the front silk screen as I told you. The silk screen is for reading the text and everything. So you can see all the other parameters like this J1, this J1, J2, D1, D2, all the naming conventions that we have made, they are visible. So in the final view, if you see, the naming conventions are visible. You can have a AC to DC converter here, and you can see our trace was on the back side. So this is how our trace is. It's visible on the back side. You can see it's uh, its edge on the edges. So the copper from the edges is removed. The center part is acting as our conducting wire. So you can think of it as an insulated conducting wire. So and now because of that, the entire plate has a copper plating and it's not eroded, and the rest of the plate could be used as grounding terminal. So you have a common ground as an entire plate, and what it would look like. So and you can also have, if you want to add some logos or names on the back, you can select here. You can the screen sizes have a logo. Maybe you can want a KiCad logo, and you can place it on the back side. There you go. You can see KiCad on the behind. Oh, and it's location. It will be it's on the back. Back screen. You can take the KiCad. You can type logo. Take the terminal. And I can put it on the back side. And see, I just changed it to dimension to back. You can change the X and Y dimension. So it's okay. If you want any text, you can add your own text. Now you can put any name you wanted. and can define it here on the back on the view. Your PCB comes with that on the back. So that's how you can define the naming conventions and everything. And yeah, that's where you can save the file for one. And now, now we are ready to export this file. So we generate a Gerber file to export. As we have seen in the home screen, we have this Gerber viewer. Okay. So here we actually generate a Gerber file. So we have to click on plot. And yeah, if you click on plot here, you just have to save the settings. You have to take a folder icon where you want to save the Gerber file. And let's define it to 3D. And payment and yeah, your future maybe that's not the need to and that is all the things are done. We click on plot on the page done, then we click on generate file. We we also check mark on generate map and I'll just use not correct and I'll generate it over there. And it's done. I close this and let me see. On my main screen, I have this AC to DC folder ready. It has all my files here with all the things, back copper tracing, back mask, and front copper trace. Everything is here. I can just choose this file and maybe choose, yeah, archive probably. You can make a zip file out of this. And now this zip file is ready to send to any manufacturer you want. It will open in Gerber Viewer and yeah, from here you can send them and get your custom PCB made. So that is all about making your own PCB. I hope I was clear in the process and like if you guys want me to, if you guys missed any part of it and want me to repeat or anything, uh, oh, sorry. Yeah, you want me to repeat any part or anything, yeah, I'm for it. So, yes, uh, yeah, guys, like if you need like any other help from my end, like any other part that you may have missed in my explanation, I can, yeah, repeat it again. And so hopefully we are all PCB designers by the end of this session, making our own custom PCB and yeah, we're ready to export the files and manufacture them. So even I am new to this PCB world. Frankly, I've learned this recently, and even I'm getting used to all things in KiCad. So this is quite new to me, but I hope we all learn and grow together. So that was the aim of this session. So eventually, we have people with enough skill and like-mindedness that we can help each other out. It could be any topic, any software that we are interested in, or maybe we want to share with each other. So
Um,
this is a good platform to do
yeah,
that.
hi,
Eventually, I
Divyam.
mean, if you're yeah,
Sorry for the interruption. Actually, I have a question from someone.
right.
Uh,
Uh,
they asked just how to install this PCB software, KiCad.
so it's quite easy. Since it's an open source software, you just have to migrate to. Uh, just show you with
Yeah, I guess the
in
link is
the
also in the presentation we would link
yeah, you
in
just
the
have to
post, blog post, but
migrate, and
you
you
can
can just
also search.
try download maybe for Windows. Just have to go migrate, select your first, operating system. You have different versions. I guess the latest one is 9. Uh, Available for version 9.0. I think you also have a guide with different versions available. Let me just find that out. So suppose if you're running an older, version or something older operating system, you can also have it downloaded from there. I think the easiest part is to get have it in the Google Chrome
I
maybe.
really don't think no one will use as old as a ERPC, bro.
Yeah, so currently I have a Windows 7 running uh, on my PC. So I was able to download it for Windows 7. So I hope you guys can have it for Windows. Yeah, here it is. Windows download. KiCad. Oh, come on. Where did that go? Usually, yeah, previous version. My bad. It was right in front. Yeah. Over here, you can just select any of the versions. I guess this 1 GB versions are the full build. Yeah. You can have them downloaded if you click it. Download the file and just quickly show. Yeah, you can just save it in your location, and based on your PC requirement, you can run KiCad 7 that would run smoothly. And if you're a Windows 7 user like me, you can have your luck tested with version 5. So that was the last supported version of KiCad for Windows 7, and I hope there are folks who would still run this. So yeah, you can always have that version downloaded and run. So big disclaimer: Windows 7 version is drastically different in not drastically, but somewhat different in UI compared to KiCad version 7 or 9. But yeah, that's up to there. Anything else?
Nothing. Perfect. And one question from my side, I would like others to answer in a chat or just by unmuting themselves. That is, what are the next sessions you want to listen? We have completed FEM. It's on the website. You can find it on the website. Now we have completed KiCad Basic. FEM is also basic. So advanced versions are gonna come. There is someone, I guess, in the viewers, I guess, who is gonna go with the KiCad Advanced also. So yeah, Divyam will also work on this. He'll also explain some. He'll explain some. There are many people who are gonna explain these two again. So any other new software, new tool which can help everyone in our career progression. So yeah, any other software tools which you wanted. Yeah, maybe we'll try the open source versions of those. And if we get the student versions or any other versions, maybe we can try with the commercial softwares like mm, ANSYS or something. Maybe. But open source is always feasible. So yeah, anyone have suggestions? Um, okay, fine. Maybe you can just ask about the suggestions on the contact form available in the blog.
Yeah. That's another way you can reach out to us.
Yeah.
Uh, so, okay, I think. maybe if no one has much to say, we can just yeah, let him and then
Good, all good. Yeah.
yeah. I hope you guys enjoyed it, and maybe most of few of you could grasp. I'm really
Oh,
sorry for any,
oh
you know,
wow. 1 minute. There is someone who's asking about ANSYS electromagnetic suite. That is a very good commercial software. Possibly, I'll try to do work on that. I'll try to have a session on that if I get a good student version or a trial version from someone. But yeah, surely I'll try. I'll try. Perfect. Yeah, sorry, Divyam, continue.
yeah, yeah. I was just saying, yeah. I think that's all I have to say. Yeah.